Hello guys and welcome back to Ansys tutorial. In this tutorial we will do some truss work, and for making truss we will use two main commands which are line from sketches and inbuilt command of Ansys which is cross section. So let's do this. Hmm. So this is experiment number 3 on trusses. Uh, I'll just show you how to make a simple truss. Get our static structurer, some Russian name, and say our project. Our project is saved. uh, yeah, done. Now let's make our truss. Go to design modeler. Let's select a plane and start sketching in it. And before sketching, I would like to introduce you to the option in the sketching under the settings tab, which is grid. Okay, so click on the both the checkbox which is showing 2D and snap. By snapping, we these grids are actually shows the dimension. Oh shit. Make sure that major grid spacing is 1 and minor grid spacing is also 1 for using grid. And let's draw our bridge. So in our question, it's given that the vertical height of this bridge is 6, 1, 2, 3, 4, 5, 6, and which is 6 meters. So this one spacing is equal to 1 meter. For checking that, we can go to dimension general, just click on this line, and yeah, look, it's 6 meter. Now go to horizontal. Our horizontal distance is 12, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Done. Now as we want to make a bridge, normally the truss angle for majorly the truss angle is 45. We will just make we will not make an angle of 45, because if we made an angle of 45 for making this truss, we'll just get two trusses like this which are connected to, and so let's just give the spacing of 2, 1, 2. It depends on what your question is and how much your specific question is. I will just be showing the technique how to do that. These were the largest minimum number of truss, which are 3, that can be fitted in this 3 sorry 12-meter base. Now let's just connect the top. Okay, and go to modify and trim this extra. Yeah, we are good now. Click generate. It doesn't matter if you click generate. And what we have to do is, yeah, now this is a sketch, and for adding a cross section we need a line geometry. Line geometry is like a path which a cross section is going to travel. It's like a swift boss base. If you use too much of if you have used the SolidWorks, not too much, just a little bit. If you have used that command, it needs a path to follow itself, but in this is not a path. It will in Ansys it doesn't take this links as a, sorry, the sketch as a path, but it will take it as a sketch, not a path. Yeah, that's was I was going to say. So for making this line sketch, uh, we will go to toolbar, and in toolbar there is an option which is called as line from sketches. Click on that. As you can see, there is a line object came there. So we'll just have to select our sketch. Our sketch was in XY plane, so open your XY plane by clicking the plus sign and select our sketch. Now as we can see, our sketch is selected. Click apply and generate. So as you can see, there is a arrows drawn on this line body. See, this is a line body, and by clicking on the line body, it says cross section not selected and none, because we actually haven't given it a cross section yet. So for giving the cross section, just click anywhere, go to concept and cross section, select the type of cross section you need. For user define, you can user define your, that is, if you there, it doesn't have a triangular cross section, and if you want to make your own type of cross section, then you can make it in a user defined. Let's select the rectangular cross section because I like to give it a rectangular cross section. And as you selected a rectangular cross section, you'll get a rectangle. Now just okay, we can sketch in this. So here there is a breadth and height of this rectangular cross section, which is actually not a rectangle because it's both sides are equal. It's a square, not a rectangle. So we don't actually have to make it rectangle. Let's just change its dimension from 0.01 to 0.05. No, I am going to make it a square, not a rectangle. So 0.05. Yeah, good now. uh, doesn't matter if you click generate or not. Oh, my sketch. Yeah, I got it. uh it's good to look at it. Yeah, now I'm satisfied. So that's it. Now it's just click on the line body by clicking on the plus sign, and now you can see our rectangular one cross section. Rectangular one, see, this is a cross section named as rect one. Now click on the line body, cross under the cross section, select the rect one and generate. Now, oh no, there is something we need to do is need to off this too, and it doesn't matter if it's on or off. Now we can't see our cross section, but it's actually there. And so for looking at, just go to view on the toolbar and select cross section solids. By selecting that, now you can see your cross section is visible. For making bridge, actually it's not in a syllabus till now, but I will still be putting it, but not now, later, in later videos, if you guys support me. Like, yeah, subscribe it please for more videos. Now our project is modeling is done. Just save it, cut our modeler, go to the model, edit. Load faster. What a potato PC I have. Yeah, my PC has just loaded our truss. Potato. Let's just generate a mesh. Wow, that's good. So minimum edge length for this mesh is given 4 meters. So let's just go to sizing, geometry. In geometry, we'll select this geometry. Can't we select that geometry? Why can't we select that geometry? Uh, Click on sizing, select geometry. Click here on the body, and yes, we've selected everything just by one click, because it's a whole body. Our work is done. Ignore this. Now go to the element size. Element size is minimum of 4 meter. I don't know why it's given 4 meter. Generate mesh. Okay. As you can see, by making it 4 meter, it just increased the size of our mesh. I don't know why it's given like that, but I will like to make my mesh finer, which is uh 0. Okay, no, not that much. 1 meter. That will be good. 100 mesh. Yeah, it's good. Doesn't need to follow everything. You can apply your own minds in sizing. It depends on you and your question. So let's give the static structurer. Now let's give the fixed support. Fixed support is given on a point which is here. Yeah, now it might be visible to everyone. Oh, sorry. Oops, headphone. Okay, that problem solved. Now let's just click on this, apply. Now that vertices is fixed, we need to apply a displacement at point B. Now point B, I am the only one who can see the point B because I have the question in my hands. 1, 2, 3. Okay, so point B is, what is point B? Oh yeah, point B is displacement. Add a displacement. Now it's very tricky. No, it's not. Just select the geometry, apply, and free. So it's free to rotate on. Just look at the global axis here. As you can see, this is the x-axis. This the structures link is parallel to the x-axis, so it should be freely moved in x-axis and be constant on y and z. So let's just make it, oh, click here and make it constant, and yeah, same to z. Click on this arrow and make it constant, and it is free to move in x components. And now we are good. No, we still not. Still need to apply forces. And at point C, which is this point, we need to apply a force. Select, apply. Now we need to apply the force of 50,000 Newton. Great. Good. 50,000 Newton of force. Now we need to apply a direction, and our direction should be applied how? Yes, our direction should be this. Oh, it's perfect. It's perfect. Direction is given, and we still need to apply more three forces which are at point D, and I don't know where this point D is. Oh yeah, I got where this point D is. D, force, and we'll apply that force on point D, which is this point. Apply. Point D is of 100,000 newtons. Yeah, just have fun. Apply the forces. Now for direction, we can choose this. No, we need to apply it downwards. So how can we apply it downwards? Can we select this both? Oh shit, I don't know how to apply it downwards. What should I do now? Select this point, this point. Okay, if we can't do that, we will do it in another way. Uh, wow, it should actually show that direction. Oh, wait a minute, I just forgot how to. Now go. Yeah, just go. Okay. Components. Okay, we got in components. We got our y direction should be 100,000 newtons. Should be constant. Okay, so now we have got our. Oh, how I did that. Oh, yes, just give it a minus sign in here. Voila, our force is applied. So, how did I do that? Let me tell you one more time. Just, yeah, just go to the define by. First, it was by vector, and we don't have an appropriate vector to define that. As you can see, we were lacking in horizontal line. So what I've did is I've just changed the vector how to define my force. So just go to define by vector and change it to components. And by changing it to components, we will see on our global axis, and global axis we need on y axis. So by keeping the other two constant, we will define our component here as minus 100,000. Done. Ramped. Okay. Functional tabular. Let it be a constant. Let both be the constant. Actually, it doesn't matter if you keep them constant on. Just select nothing. Just keep them zero. And done. Our force two was is applied now, and we still need to apply two more forces, and which is on. Oh my God. What was the force on C here? Okay, oh no, the C component is also downwards. It's my mistake, sorry. Let's change it to vector. Let's change it from vector to components. And it was y-axis, which is minus 50,000. Yeah, we are good. And just go and check one more time. It's still better. Force 2 is applied. Our CD is done now. It's time for point E. Point E is of 80,000 newtons, and which is that point. So let's go here, insert force, select this point, apply. We will now define our direction. Oh no, the just first give it a magnitude of 80,000. Done. And the direction, it is simple because we have a horizontal direction and it's perfect. Just I have selected this edge for any horizontal edge for direction purpose. Done. And at point F we need to apply 8,008 kilonewton of force, which is 8,000, and point F is behind point. So let's just apply, insert force, select this edge. Sorry, that's a vertex, not a edge. The line between two vertices is a edge. And the 8,000. Yeah, and now let's define its direction, and its direction is similar to this. Select this edge, apply. Or the hell? Oh, that arrow is so tiny. That's so tiny that I can't even see that. Are we done? No, we still not done. We now have to. Yeah, no, we are done actually, but we still are not done because we need to simulate it. And what we have to find out is, it must be given in a question. I'll just find out what I love, and I like to see the deformation because it's so colorful, and the only thing I can understand clearly is deformation. And we will beam tools. Yeah, beam tools is what I have not s- uh, given introduction in tutorial. You can directly import beam tools, and in beam tools you will directly get the direct stress, the things we calculate, maximum on the beam, are required to design a beam, which are direct stress, minimum combined stress, and maximum combined stress. Now let's just solve it by right clicking on solution and solve, or you can click F5. It's a shortcut. And wait for him to solve the kilonewtons and 1,000 kilonewtons of forces. Yes, now it has solved. Everything is green. Let's see the first thing I understand the most, which is total deformation. And yes, look how deformed it is. And I always like to see its animation. Now, as you can see, uh, wait a minute, how to get normal. Okay, it doesn't matter. I will make it normal. As you can see, we have fixed our this point. We have given displacement to this point in x direction. We have applied forces in here and here, here and here. So our forces direction for these 2 points were in that direction, which is x direction. Our force direction for this was downwards. Our force direction for this was also downwards. So as you can see, the deformation for this bridge should be taking place like this, and the maximum deformation was 0.024741 meters. The unit is given above, and minimum value is always zero. Okay, so deformation at here is zero. By colors you can see. Okay, let me just stop this. Stop. Yeah, and by colors now you can see that blue area is where we have zero deflection deformation. Okay, and orange area where the deformation is about 0.0019, that is 0.002 meters of deformation, which is I don't know, large or quite high. And here the deformation is maximum as we applied 80,000 newtons of force here. So it's quite obvious that it will deform too much, and maximum force applied was here. So let's get the direct stress. Let's analyze the direct stress. So direct stress induced is higher in, yeah, in this beam. direct stress. So for reducing this, we can, if this you think is too much or maximum, we can increase the thickness of our truss, sorry, our cross section, and we can analyze it one more time. So for overcoming our overcoming our design of this truss, and for minimum combined stress, it's still the same. Maximum combined stress, it's again same. A beam tool doesn't help too much. Okay, that's it for this tutorial, and please subscribe me by subscribing, and also comment in the comment box below. So, and let me know if my voice was clear, my accent is good or not. For these videos, I'll try to overcome that problems. I know that problems hurt too much. I have a shitty mic too, and potato PC, which helps me a lot for making these videos. So what should I do? Yeah, thank you for watching, and I see you in the next video. Bye bye.